Dear friends, welcome to the 14th video lecture on differential geometry course. Today I'll start with the lemma we stated and proved last time. Uh, for the sake of completeness, I will state it here one more time. And it was this: if M is a connected all umbilic surface, this means all the points of M. In other words, every point of M is umbilic. Okay, then M has constant Gaussian curvature, and the curvature is positive. Of course, once it is constant, it is positive. It is non-negative because umbilic means principal curvatures K1 and K2 are equal to each other, and Gaussian curvature is the product of these two curvatures. In this case, it will be just K1 squared. Therefore, it is non-negative. So we proved this last time. We will continue from this point. Here is another result. At the end of three results, we will show that if okay, so if it is all umbilic, then M is a part of a plane or sphere. So that will be our final result. This is another step in that direction. So let me just state this. If M is all umbilic and K is positive, then M is a part of a sphere of radius 1 over square root of K. Okay, let's see the proof. Well, let P be a point and consider the point C given by this P plus 1 over Kp times the vector E3P. Okay, where E1, E2, E3 is an adapted frame. Frame on M, and Kp is equal to the since it is all in umbilic, common normal curvature or principal curvature, sorry. Okay, let Q be any other point on M and choose a curve alpha defined on the interval 0, 1 with starting point P and ending point Q. Okay. Uh, Also let gamma t be the following curve. Okay, gamma t be the curve given by so alpha t plus 1 over the curvature times E3 gamma t. So I just look at take this point and here replace p by alpha t. Okay, that's it. Okay. Now by the previous lemma, uh, Kp, which is K1p, K2p Gaussian curvature, is a and which is equal to K squared p is a constant function. Constant function, right? Thus, if I take the derivative, thus this is equal to what? Alpha prime t plus, well, k is constant no matter what you put inside. So 1 over k alpha t uh, will we will regard it as a constant, and let me just write k there. And then derivative of this, well, that is just e3 prime. So derivative of this, we denote it like this. However, here e3 prime is of course our normal vector, so it's u prime, and we know that this is just s of alpha prime t, and uh, any direction is principal, therefore this is just this. Any direction is principal because all points are umbilic, therefore k1 equals to k2. In other words, our shape operator is a scalar times the identity operator. So that S is a scalar function. Because k is also constant. Okay, k is constant. Thus, we get this gamma prime, which is just alpha prime 1 over k, and then instead of this, I will just write minus k times alpha prime. But this is minus alpha prime plus alpha prime, so it is 0. So that gamma is constant. Constant. This means what? This means so C, which is gamma 0, right? When you plug 0 for t here, when you plug 0, you get alpha 0, and then k, and then you get this, which is C, right? So when you plug 0 here, you get exactly here should this is alpha, sorry. So when you plug 0, you get p here, p here, p here, exactly this expression. All right. So you get this, but since gamma is constant, this is equal to this gadget, and this is just this. Hence, okay, the distance between the point C, gamma 0, and point Q, the Euclidean distance is just the norm of this vector, but E3 is a unit vector, therefore this is just 1 over K. So, and this is true for every Q in M. Well, this means uh, our surface at a distance from C, where the distance is 1 over K. In other words, M is a part of a sphere with center C and radius 1 over K. Hence, M is uh, contained in the sphere of radius 1 over K and center C. And this finishes the proof. Note that 1 over K, the common normal curvature, principal curvature, this is just 1 over the Gaussian curvature, which is a constant number on the surface. And the proof finishes. Okay. So this shows what? Hence, uh, uh, we get the following corollary. A surface M is all umbilic if and on if M is a part of a plane or uh, a sphere. In particular, if M is compact, then it cannot be a part of a plane. Therefore, it has to be a sphere. If M is compact, then M must be a sphere. Okay. Okay. Yeah. So we obtained this result. Now our next result, again a global fact, is the following theorem. So far we have proved the following. If a surface is all umbilic, then Gaussian curvature is constant, and that implies that our surface is a part of a sphere. Of course, there is the case that M can be a part of a plane. In that case, it is all oblique, but this time Gaussian curvature is identically 0, and the shape operator is just trivial in that case. Okay, let's see what this theorem tells us. On every compact surface M in R3, there is a point at which the Gaussian curvature is positive. So if you have a compact surface in R3, there is at least one point at which the Gaussian curvature is positive. Okay. Let's see the proof. Well, this, of course, maybe let me write a corollary of this. Immediate corollary. There is no compact surface in R3 with Gaussian curvature is always negative. Okay, there's no such surface in R3. Compact surface, of course. There are non-compact surfaces where Gaussian curvature is always 0 or negative, but there's no compact surface. All right, let's see the proof. Of the theorem. Well, the idea is very simple actually. Since this surface is compact, it is bounded. It's a surface like this. You measure the distance from a given point, let's say from the origin to this surface, and look at the maximum value of this function. Let's say it is here. So the point with maximal distance to the point to the origin. So let's say it is here. We will show that if this is the point with maximal distance, then at this point, this surface looks like a sphere. Therefore, it has positive Gaussian curvature. That's the strategy of the proof. All right, now let's see the details. Okay, so let f R3 to R be the function given by f of p norm of p squared, so the distance function, square of the distance function. Since f is continuous, and m is compact, the restriction of f to m has a maximum value. Say at a point m. Let's say it is this point. Okay. All right. First claim is this. Let R to be the distance of this point to the origin. I can assume that this is positive because this is the farthest point. If it is 0, it means M consists of a single point, which is the origin. But M is a surface, so it is two-dimensional. It cannot be just a point, okay? So that's why R has to be positive. So R is this distance. All right, let's continue. Well, the conclusion is this. Then, if R is this distance, then Km, the Gaussian curvature, is larger than, at this point, 1 over R squared, which is positive. And this finishes the proof. Right? So note that the claim proves the theorem. Now let's see the proof of the claim. Okay, for this, let U be any vector to the surface at this point. So U is a vector like this. Okay. Uh, and choose a unit unit, sorry, not speed, unit vector no, no. Let U be a unit vector, sorry, unit tangent vector, and choose a unit speed curve alpha on M with alpha 0 is M and alpha prime 0 is U. So we choose a curve passing through this point and the velocity vector U at this point. Okay. Well, let's see how things go. Well, this implies what? Thus, the function, which function? F of alpha t has, so this is, remember, norm alpha t squared, has its maximum at t equals 0. Thus, from the uh, first year calculus, we know that in this case, the first derivative of this function at 0 is 0, and the second derivative, since this is a maximum of this function at 0, is non-positive, since it has a maximum. Well, now let's write down this equation one more time. 0 is equal to uh, derivative of f of alpha t at 0, but this is just alpha t dot product with alpha t, derivative of this evaluated at 0, And we know that this is just 2 times alpha 0 times alpha prime 0. And this is equal to uh, 2 times, this is just m, and this is u. So the vector u dot product with m. Here I consider m as a point on the surface, but here, of course, it is the vector joining that point to the origin. So I regard this m also as a vector, right? So m is this vector here, u is this vector, and they are, of course, 0. Product is 0. So this means what? Hence, since u is an arbitrary point, arbitrary vector in TPM, we see that M is perpendicular to every vector in TPM. We see that U is perpendicular to the whole tangent space. Okay. Okay. What about the second inequality? On the other hand, we have this second derivative of this is equal to, right, this is alpha dot alpha, so first derivative was this 2 alpha alpha prime. I take derivative one more time, so we get 2 times alpha prime dot alpha prime plus 2 alpha alpha double prime, and hence if I plug 0, so alpha prime 0 dot alpha prime 0 plus 2 alpha 0 0, this is negative. So we get this. If I plug, this is u dot u, and then u, not p, no, m dot gamma double prime. So I have this u dot u plus m dot alpha double prime 0 is negative. Okay. But u is a constant vector, sorry, unit vector. So this is 1 plus m times dot product. This is negative. And from this, we get what? M dot this is less than minus 1. Okay. Since length of m, the vector m is r, right? Remember, r is the length of this vector. So if I divide that vector m by r, I get a unit vector. M over r is a unit normal vector to m at this point. Okay, but we know that we get from this the following: ku, the normal curvature uh, for this vector is what? We know that this is just the unit normal at that point times uh, the second derivative. Right here, u is just, remember, uh, this vector. So I know this, and therefore, okay, let me write here. So this is just, let's see, uh, this is less than minus 1. So if I divide by r, I will get minus 1 over r. This is since alpha 0, alpha prime 0 is equal to u. Okay. All right. And this is true for all uh, unit vectors u in TPM. Okay. So in particular, the Gaussian curvature at M, which is just K1 U times K2 U, but each one is less than 1 over R, therefore their product is greater than 1 over R squared. Okay. So this, of course, proves the claim and therefore the theorem. Okay. All right. Let's see how much time I have. Okay, I still have some time. Uh, this is a very, nice fact, global fact about surfaces. Uh, we have another result, a lemma called Hilbert's lemma, disproved by Hilbert. Okay, so this is a technical result. Let M be a point of M in R3 such that the following happen. K1 has a local maximum at M. So the larger uh, principal curvature has a local maximum at K1, and K2 has a local minimum at M. And the third condition is that, okay, let me write it this way, has a local minimum at M. And finally, uh, let's say we know that, of course, K1 is the larger one, but it is we assume that it is strictly larger than K2. Then the conclusion is that Gaussian curvature at this point cannot be positive. Okay, let's see why this is the case. Well, uh, since K1M is larger than K2M, right? This is the assumption. M is not an oblique point, and thus by a previous lemma, uh, there is a principal frame. There is a principal frame E1, E2, E3 defined on a neighborhood of M. Right? We proved this fact before. This principal directions, principal frame is determined by the eigenvectors of the shape operator. All right. Now, here is a fact which we will need. This is again a side remark actually. Let f be a function on M so that f has a maximum or minimum at a point P. If V is a vector at P, then tangent vector, of course, then we have this. First, V of f is 0 because it's a local extreme value. And the second, if I take derivative of f twice along this vector, I get 0 negative number or positive number respectively. So if f is a maximum, then this is negative. If f is a minimum, then it is positive. So this is a fact from calculus. Here, just note that this is not just standard calculus fact, because we are on a surface and we don't have f prime, but we have directional derivative of f. So we just take derivative of f along the vector v, and as you just go on the surface in the direction of v, and if you are at the point P, and if this is the maximum value, then this is 0 and the second derivative has to be negative. If it is minimum, then the second derivative should be positive. So, hence, by this fact, we have this E1 of K2 and E2 of K1, they are both 0 at M, because K1 has no, what was this? K1 had a maximum at M and K2 had a minimum. So they have both extreme values. Therefore, these are 0. These are 0 actually for all vectors, but in particular for K1 and K2. And the second derivative of K2 along the vector of K2 along the vector E1 is positive, and the second derivative along the vector E2 of K1 is negative at M, because K2 had minimum and K1 had maximum, right? So, okay, yes, okay. Now, from the Kodazi equations, which says that, let's recall what the Kodazi equations tells us. It was this. There are two equations. E1 of K2 was K1 minus K2, and then W1 to E2, and the second quadratic equation E2 of K1 is K1 minus K2, W1 to this time E1. Uh, we obtain, so if I plug all these, we get what? So this is 0, and this is not 0. K1 and K2 are not equal to each other. K1 is strictly larger than this. Therefore, this is 0. And so W1 to E2 is 0. And again, this is 0, but this number is not 0. Therefore, this real number is also 0. We obtain that both of these are 0. So W1 to E2 equals W1 to E1. They are both equal to 0. Okay, because K1 is larger than K2. So that the difference is not 0. Okay. Now here I will use the fact proved in the exercises. So I leave it as an exercise. So this is an exercise. I will leave it as an exercise to you. Exercise 2 of section 6.2, and it tells us this. Gaussian curvature is E2 of W1 to of E1 minus E1 of W1 to of E2 at the point M. So Gaussian curvature is given by this formula. Now, okay. Now take the first quadratic equation and apply star, E1 to the first one. So apply the field. So you just take derivative of the first equation. Apply the field E1 to the first quadratic equation to get what? If I apply E1 to both sides, I get E1 of K2, right, is equal to E1 of this. So E1 of K1 minus E1 of K2, and then omega 1 to E2 plus, right, we apply Leibniz rule, K1 minus K2, and then E1 of this. What is E1 of this? So let me write first E1 of W1 to E1. This is a function, so I take E1 derivative of this. All right. Well, however, at the point M, we had W1, 2 was 0 because, you know, this one form is 0 on both vectors. So it is 0 at all the vectors, right? They form a basis, so the one form is 0 identically. And K1 minus K2 is positive. Thus, we see what? So this is 0. Therefore, no, not this is 0. This thing is 0. Sorry. This thing is 0. And this number is positive. So we see that that's okay. So this is positive. Therefore, we see what? This thing is a positive number times this gadget. But we know that E11K2 was what? Let's see. E11K2 was positive. So this thing is positive. This number is positive. Therefore, this has to be non-negative. Thus, E1 of W1 to E1 has to be non-negative. Okay. Uh, Similarly, taking E2 derivative of the second Kodazi equation, which is this thing, the second Kodazi equation, we obtain similar consideration gives us the following. E2 of W1 to E2, sorry, E1 is negative at M. Let's see. No, it should be E2. Okay, so this should be E2. Okay, but then let's look at this exercise. Exercise tells me that Gaussian curvature is the difference of these two gadgets, and we know that the first one is positive, and the second one is negative, right? Sorry, E1 W1 to E2. So you subtract from a positive number, non-negative number, a non-positive number. What you get is a non-negative number. Hence, the proof finishes by star. Star is, let's say, no, here. Yes, that is this. Okay. So this finishes the proof. Okay, let me see how much time do I have. All right. Let me stop here. There is one more theorem I need to prove in this section, but I'll do it next time. So see you then.